Now in today's session, let me learn about this second type of flip-flop, which is your D flip-flop, data flip-flop, or transparent latch, or delay flip-flop. So why it is having these all the other names that we are going to learn in today's session. So now why to prefer your data flip-flop? So how it is constructed using your SR flip-flop. So now the drawback of your SR flip-flop is, so in order to eliminate your drawback of your SR flip-flop where S input R input is equal to 1. So when your S input R input is 1 in your SR flip-flop, so we obtained an invalid state or a forbidden state in your SR since of your both outputs now they are becoming logical 1. Q1 is equal to 1, Q1 bar is also equal to logic 1. So in order to avoid that forbidden state, so since it is not obeying the complementation law, so we treated those states of F for S input R input equal to 1 is treated as your invalid state. So that invalid state how to avoid in your data flip-flop is, so here not to make that, so S input and R input must be equal to logic 1 at the same time. So in order to do that, so always this S input and R input must be complemented to each other. So we have introduced a NOT gate in order to obtain that configuration where your S input and R input must be complemented to each other. So by connecting this NOT gate, so here I used a NAND gate which is functioning like a NOT gate. So when S input is equal to 0, so R input now it become logical 1. Since I connected the input of your NOT gate as your S input and output of the NOT gate is connected to the R input end. So hence here if S input is 0, R input is equal to 1. If S input is equal to 1, so due to this NOT gate it is complemented and that is applied as your logical 0 output. So in that, so after connecting this complemented output of your NOT gate as the input and the input of your S, so let I take the common input which is equal to D input. So let I treat this as a data input or your delay input. So here now let me learn about, so why we have set this as a data input or your delay input. Now so when our data input is at 0, so set input now it become logic 0, reset input is equal to 1, enable signal or your control signal when it is 1, then it will allow your external input to change the output of your sequential circuit. So if it is having 1 1 on your second AND gate, the output of your second NAND gate now it become transferred with a 0. So here one of the input is 0, enable input is 1. So first NAND gate output become logic 1. So now if I treat your present state is 0, complemented state is equal to logic 1. Since of this input which is transferred from your second NAND gate to the fourth NAND gate. So here the output of your fourth NAND gate is shifted to logic 1 and that one is transferred as your input to the third NAND gate. And now the third NAND gate output would generate your next state which is equal to 0. So now present state if it is 0, the next state is a 0. The same manner, so let I take the D input 0, present state if I assume 1, the complemented state is logical 0. So data input 0, since that set input 0, reset input is 1, enable input is 1. So output of your second NAND gate generates the 0 output. First NAND gate it generates your 1 output and that output is transferred as your input to the third NAND gate and this 0 output of your second NAND gate is transferred to the fourth NAND gate. Now here due to this 0 input, the output of your fourth NAND gate is shifted to logic 1 and now so 1 1 is shifted to your 1. So here 0 is 0 due to this 0 input. So fourth NAND gate output is shifted to your fourth NAND gate output is shifted from 0 to 1 when it is transferred 1. So then here we would obtain your logical 0. So now here for the present state of logic 1, your output state when data input is 0, it is equal to 0. Next, let it read your next state which is equal to data input is 1. So since data input is 1, set input is directly connected as data input and that inverted data input is connected as your reset input. So here reset input become logical 0. enable is equal to 1. So because of two logical ones on your first NAND gate, output of first NAND gate will generate 0. And because of one of the input is 0, second NAND gate will generate the logical 1 output, and that is transferred as your input to the fourth NAND gate. And here first NAND gate output is transferred as your third NAND gate input. Now let us assume your present state is 0, complemented state is 1. So since of this 0 input which is transferred from your first NAND gate, output of your third NAND gate is shifted to the next state with the logic 1, and if that 1 is transferred as your input to your fourth NAND gate, now your complemented next state become logical 0. So for data input of 1, if my present state is 0, next state is a logical 1. The same manner, so let us assume the next state of your present state as your 1. So complementary state is 0. So the same applied input of D equal to 1, S equal to 1, R becomes 0, enable equal to 1. So first NAND gate output is 0, second NAND gate output is 1. Now output of your third NAND gate is shifted to the next state which is equal to logic 1, since of the first NAND gate output is 0, that is applied as your input to the third NAND gate, hence it is enabling its next state with a logical 1, and that one is transferred as your second input of your fourth NAND gate. Already it is having one input, so both inputs are logic 1, and the complemented state is now transferred to the 0 state. So now by just observing this truth table, we came to know that so Qn plus 1 is exactly that of your data input. So hence it is your next state is transparent to the applied data input. If D is 0, your Qn plus 1 is 0. If D is 1, your Qn plus 1 is also equal to 1. So output is, or the next state is transparent to the data input what you apply on your D flip-flop. So hence it is called as your transparent latch. Or so after some time delay, after the one clock cycle of your clock period, you obtain your, or the data input is transferred to the output of your sequential circuit. Hence it is called delay flip-flop. So after one clock pulse of your circuit, so you can obtain your output which is exactly that of your data input. So hence this is also called your a delay flip-flop or your data flip-flop or the transparent latch. So now, so the first diagram which shows the block diagram of your data flip-flop. So here only one data input with the addition of your clock signal, asynchronous inputs preset and clear, and two outputs which are complemented output as well as your uncomplemented output. And now just small modification done in your SR flip-flop in order to obtain the D flip-flop logical diagram. We have been connected S input directly as your data input, and then so using your NOT gate or using an AND gate which can function like a NOT gate, that is connected to the reset input. So in order to make sure that in order to have your S and R inputs must be equal to logic 1 to avoid your forbidden state. So we have been connected so a NOT gate in between your S and R inputs. So when data input is 0, output of your next state of your flip-flop is exactly equal to data input which is logic 0. When data input is 1, so Qn plus 1 or your next state is equal to logical 1. So like this, so we're going to define the state table of your clock data flip-flop, and now we avoid that, so there is no possibility that S and R inputs both become logical 1. So we avoid that invalid state of your SR flip-flop in your data flip-flop. From this data flip-flop state table, let me derive your characteristic equation of your data flip-flop. From its state table, Qn plus 1 is written as a function of your present input D and its next state which is Qn. So which is equal to sigma m of 1, 2, comma 3. So here the functional values are, the min-term functional values are 1, only the combination of your 2 as well as the combination of your 3. If I write that in a as a decimal code. So sigma m standard is in the standard SOP form. As a sum of minterms, you can write it as m2 plus m3 or sigma m of your 2 comma 3. So hence here, if I map your function on a two variable, the suitable two variable came up. Always here two minterms are there on your second cell as well as on the third cell. This is two square adjacency which can form a pair, and this pair is having the common variable d, where the q1 value is different for this two minterm. Hence the characteristic equation q1 plus 1 is equal to d. So characteristic equation is nothing but next state derivation. So which is represented, it's a relation between your present inputs and your outputs. So it will give you the relation between the present inputs, how it is dependent. Your next state is dependent on your present input and present state. So qn plus 1 is equal to d. So exactly the next state is equal to the data input what you apply on your data flip-flop. From this state table, let me derive your excitation table. In this excitation table, we have a state transition of from present state to next state. As 0 0, d input is 0. Next 0 1, d input is 1. So 1 0, 1 to 0, d input is 0. So 1 to 1, so your d input is equal to logic 1. So this excitation table, this is the excitation table of your D flip-flop. Now by observing your values of the un plus 1 and d, exactly they are same. So un plus 1 is equal to d. So hence it is also known as your transparent latch out. Your next state is transparent to the applied input. So hence it is known as your transparent latch, or it is equal to data input, exactly that of your applied data input. So hence it is also called as your data flip-flop. Next, after a one clock pulse, you can obtain your output exactly that of your input. So after that time delay of one clock, you would obtain your output which is exactly equal to the data input. Hence it is also known as your delay D flip-flop or your delay flip-flop. So this is about our today's session. So in next class, so we are going to learn about your JK as well as your T flip-flops.